and a quick overview on the ISO 25119 standards that is related on the safety for tractor and forestry and agricultural machines. Okay. Let's start with a quick overview of what is a definition of what is the functional safety. Okay, as reported in the IEC 61508, the functional safety is the freedom from an acceptable risk of physical injury or damage to the health of people, either directly or indirectly. Why the functional safety is so important today? Because the increase of machine automation and complexity require strong safety requirement to ensure that in case of malfunctioning, the risk for people health are reduced to an acceptable threshold. In this slide, I'm showing you a brief overview of the safety standards and regulation that are involved in the functional safety for vehicle and machinery. On the top of the diagram, there are the, let me say, the standard that introduce general regulation or methodologies to design and to develop functions that have an impact on the safety of the people. We have the risk assessment standards, the ISO 12100, the machine directive that say a set of prescription that every machine that are sold on the European market have to be must fulfill in order to be sold in Europe, and the safety of machinery with the 61508 on the ISO 13849 that describe a set of general requirements about the safety. But as I said before, those standards are too general for the application, or it may result too difficult to apply those standards, and therefore have been developed a set of specific standard for each compartment, for the different industry compartment. You may know the safety standard for the automotive, the ISO 26262, and for the railway, for the moving machinery, and the ISO 25119 is the standard specific for agricultural and forestry machine. Those standards introduce a set of specific requirements and work product that manufacturers must produce, must fulfill in order to have the compliance, to require the compliance about functional safety on the system that they are developing. The ISO 25119 is applicable only is enough to the safety related parts of the electrical, electronical, and programmable electronic system. So it covers all the electric and electrical part of the machine, of the machinery, and not the mechanical part. So it's related to the safety of the electronic. And it doesn't cover all the other hazards that are there are specific standards for other hazards. Let me say, for example, for electric shock, for the fire, for the ergonomics, or corrosion, electromagnetic compatibility, and so on. But it's not the context of this standard. There are specific standards about those hazards. And the use of ISO 25119 is voluntary, so the manufacturer can use other standard. I showed before the more high-level standard, more general standard about the safety. Manufacturer can provide, can use other standard, but they have to provide evidence that um, the approach that they have used meet the essential requirements that are also reported in this ISO. The, the standard is divided into 4 parts. We have part 1 that introduces the general principles, the normative reference, terms, definition, and some other generic, even introduction about the 10119. There is the part 2 defines the concept phase, so all the methodologies, requirement, and the work product that have to be provided during the concept phase of the development of the machine. There is the part 3 that describes the requirement about hardware, software, system design. And the last part, the part 4, regards the production operation, modification, dismissing of the system. So the standard covers the whole life of the machinery, from the design, from the concept phase, to the production, and to the development, and to the production and dismissing of the system. So it defines a safety life cycle, and yeah, this safety life cycle follows more or less, no, not more or less, but it is a derivative of the widely used V model that is common in many other standards. So a development process, the process must follow the V model, where there are for each design activity there is a parallel verification or validation activity that have to be performed in order to go on with the process. So, as I said before, the standard those define all the requirement from the cradle to grave life of the product system. Here there is a diagram that show more or less what I said before. So the different part of the process. From on the top, there is the concept phase, where we have some tasks that have to be performed. On the center, there is the series development, so the system design, hardware, software, product release, and other things that have to be done during the development. And on the bottom, there is the management of the production, the maintenance, servicing, repair, and the commissioning, or the change management for modification. We can see that on the left there is the management of and assessment of functional safety that must cover all the part of the life of our system. Here there are the details, the cycle related to system design. We can see that start from on the left, from the risk analysis to the specification of system requirement, and the design, the technical refinement of the requirements. And on the right side of the cycle, there are the verification activities that must be performed before to go on with or during, or at the same time, when we follow the process, the development process. As I said before, in the previous slide, the V model related to the system design. Here there is the V model for the hardware design. So the standard is gives to the manufacturer a detailed series of activities, work product, and the verification and validation activities that have to be performed in order to validate, to ensure the safety of the product. So we have the activities for the hardware and for the software. So it's not only a general V model, but is a V model declined for system design, software, and hardware design. So is quite, I can say that is quite detailed. One of the most important part of the safety life cycle is the risk analysis, the risk assessment, and this phase aims to identify the hazardous situation that can be generated by a malfunctioning of the safety function, and usually involves people from different departments, electronic, electrical, testing and validation, and so on, in order to analyze and identify all the hazardous situation that can be generated by our system. So the risk analysis is based on several factors, 3 factors especially. The first one is the severity. So when we analyze the hazard, the risk, we must consider the severity. So what is the harm that can be generated by the failure of the system? The severity shall be considered for each relevant scenario. So on the road, on the field, on the garage, in confined area, and so on, in any relevant scenario that the manufacturer define and in a relevant scenario. So we start from the S0, from the lowest severity, that is the level S0, to the S3, which is the life-threatening injuries and the death of the operator, of bystander, of other, or no? And another factor that we must consider in our risk analysis is the exposure. So the frequency, the probability for how much our system is used. So the exposure is how often and how long the operator, bystander, and other people are exposed to the hazard where a failure could result in an injury to the operator or bystander. So we must consider the severity, the exposure, and the last one is the controllability. So it is the capability for the operator to control the dangerous situation and avoid the dangerous situation. So we must have a system or a failure that is easy controllable. So we give to this hazard a rate of C0, but we can also have an hazard that is unavoidable, and so we give to the hazard the C3 value, because there is no way to avoid the hazard in case of fault. So, as I say, once we have all the three estimations, severity, exposure, and controllability for each scenario, we can determine the agricultural performance level required by the function. The agricultural performance level is one of the most, the AgPL is one of the most important things, terms that is present in the standard, and is the probability of the risk. It gives a value to the to our system that have on a scale from level A to level E, and on the basis of the agricultural performance level, we have more demanding or less demanding system requirements, safety requirements that have to be fulfilled in order to guarantee, to ensure the safety of our system. So we can say that on the left there is the diagram that show on the basis of severity, exposure, and controllability, which is the value, the resulting value for the AgPL. So we have performed the risk analysis. We have obtained the value of agricultural performance level, and this level is a probability of failure. It's the residual probability of a dangerous failure, and we can say that it can be compared to the performance level defined on the safety integrity level, the SEAL, that maybe some of the ASIL level that maybe some of you may know. There is an equivalence between the performance level defined by the 25119 to the performance level of safety integrity level defined in other standard. The common the point is the common ground is the probability of dangerous failure per hour, that we can say different standards call the performance level in different way, but the important thing is the probability of dangerous failures, which is the same for different standard. So and there is a table, a comparison table. So once we have the agricultural performance level of our safety function, we have a set of requirement, a set of constraint that we have to follow when we design our system, and the performance level is can be split in 4 aspects that are the main time to dangerous failure, the diagnostic coverage, the hardware categories, and the software requirement level that concurs to that we must consider when we design our system, because the same performance level can be obtained by different combination of system design. So on the a quick recap, on the left we have the risk assessment. We found the resulting performance level, so performance level A, B, C, or D, and how we have to design the system once we have the performance level. Okay, on the other diagram there is the specification that there is a diagram that show that for performance level A, B, C, D, E, there are different combination of diagnostic coverage, hardware category, MTTFd, and software requirement level that our system must fulfill. So I don't know if some of you are already familiar with the terms MTTF, diagnostic coverage or category, and so on. But in any case, I will quickly explain what does it mean MTTF, hardware category, and so on. So the MTTFd is the average value of the expected time to a dangerous failure. So it more or less define the quality, the robustness of our hardware, and the MTTFd. The MTTFd is the dangerous percentage of the mean time to failure of our device, of our components, and it can be obtained and derived by standard database. There are many standards that reports the average or statistical evaluation of the mean time to failure of a specific component, resistor, capacitor, integrated control, microcontroller, and so on. And it's not easy to estimate, to calculate the actual MTTF of our component, of our system, because it's composed by many different components, and we can estimate. Usually, the manufacturer estimate the MTTFd assuming that the 50% of all failures are dangerous, but there are more quantitative methods that can lead to a precise determination of the mean time to dangerous failure. Is up to the manufacturer refine or not the calculation of the MTTF. Another important thing is that diagnostic coverage is the fraction of the probability to detect dangerous failure and the probability to total dangerous failure. So diagnostic coverage helps. The aim of diagnostic coverage, as I said before, is to determine how many dangerous failures we are able to detect, and on the total of dangerous failure of our system. The standard gives three values of diagnostic coverage: low diagnostic coverage, when we are able to detect less than 60% of all the dangerous failure; medium; or high, if our system is more or less cover more than 90% of all the dangerous failure. But probably the more interesting concept exposed in the ISO 25119 is the hardware category concept. The MTTFd, the diagnostic coverage, are concepts that we can say that are quite common, or at least in my experience, more or less are reported in also in other standards. But peculiar to this regulation is the hardware categories. The hardware categories is a suggested architecture for that we have to use. It's not suggested, we have to use it in or give the evidence that we follow the prescription defined in the by by the required hardware category in our design, and is a suggested architecture that have to be used in the implementation of our safety function. What does it mean? We have 4 categories from the category B 5 categories from the category B to the category 4. And we can see that category B is the simplest architecture to the category 4 that is a fully redundant architecture. So we have the example what the standard define as hardware category B, and the properties of this hardware category are to have a low diagnostic coverage, so less than 60% of dangerous failure are detected. The MTTF for the D for the channel, so for the input logic, for the combination of input logic and output, can can go to low, from low to medium, and this is the most is the simplest architecture that we can imagine for our system. It is composed by an input, a logic, and an output. Usually, this architecture, the B, is only used for for low demanding safety function. For simple system, we have a refinement of the category B, which is the category 1. Is more or less the same that the previous category, but so a single fault on the chain on our safety path input, a single fault on the input or the logic or on the output can lead to the loss of the safety function, but we have an improved diagnostic coverage. The hardware categories 2 is more interesting, and we can see that in addition to the standard chain of input logic and output, we have a test equipment and output test equipment that shall detect any fault on the logic or on the input. So they have to implement a continuous monitoring of the logic and of the output. And so we are able to reach a safe state, to shut down safely our function in case of fault, because we are able to detect. We have we have an improved detectability of failure. In addition to the category 2, there is the category 3, where we have we have a redundancy. We have two chain, input 1, logic 1, output 1, and the redundant safety path that this architecture is suitable for a single point fail operational system. So in case of a single fault the redundant part can provide the functionality, maybe with a reduced performance, but we do not lose completely the safety function, but and so our system is fail operational. The last one, the hardware category for defined for the highest for the higher performance level is the hardware category 4, which impose redundant input logic and output, is similar to category 3, but have the highest diagnostic coverage that must be high. So it can be considered fault tolerant, and gives a greater and lead to a greater dependability of our safety function. So we have seen the hardware category, as I said before, are suggested architecture for the design of our system, for the hardware and for the system design of our system. And in addition to this, the standard gives also some requirement on the software. So defines requirement for the software architecture, for the software module design, and for the software testing. As I said before, for the software requirement level called SRL, space from goes from safety requirement level B to the safety requirement level equal to 3, and where more demanding methodologies, testing, and techniques have to be applied in order to have the compliance with the specified software requirement level. So you can see that for there are techniques like informal design methods or semi-formal design method or formal design methods. And for instance, for the safety requirement level greater than 2, equal or greater than 2, the informal design methods are no more allowed, but we have to switch to semi-formal or formal design method, give more guarantee about the quality of our software, not the quality, but the quality of our requirements. And on the same is the same for the design and implementation of our software. So when we have on the SRL 2 or 3, we have to use strongly typed programmed languages. For instance, it's recommended to use strongly typed programming languages, follow formal design method in the design of our software module. Maybe for the no maybe, but also we have to use technique defensive programming technique if our performance level require the use of SRL3 and so on. We can see that the software becomes more complex if we have to fulfill SRL, greater SRL, also for the design, for the test. No, this slide is also about software design and implementation. We can see the prescription that are required for the software requirement level 3 are, in my opinion, quite demanding. So we have to limit the use of dynamic variable or object, we limited use of interrupt, no recursion, defined use of the pointer, and so our software becomes very more complex to design. Also for the testing, we can see that there are several tests that have to be performed, and we have to give the evidence that we have made all the software, all the testing activities required by our software requirement level. So from static analysis to performance testing and from functional and black box testing, depending on the software requirement level, we have to perform several activities. And in addition to this, we have to give the evidence of that safety, the safety related part of a software is independent from other software that is not safety relevant. So we have to give evidence of the software partitioning. So non-safety software, a fault, an error on our in the non-safety related part of our software must not influence the safety related part of our software. So no memory corruption, blocking of different partition, allocation of the processor execution time, and so on. So we have to give evidence that our safety software is independent from the other software on of the system, on the same system. Another important point that we have that is defined in the standard is the estimation and of the common cause failure. So if we have redundant redundant architecture, we must be sure that there are no common cause common point of failure that can affect both parts of our architecture. And the ISO gives us a checklist that we have to review, a checklist that defines a score for the measure that we use to protect our system from the common fault failure. For example, the physical separation between signal and power paths. So we have to be sure that we have different, for instance, power supply in a redundant architecture. Otherwise, a single fault on the power supply can shut off the whole system, and it is not good. We have to use diversity, so the diversity in the design of our architecture. We have to perform several measures to protect, to give to ensure the robustness of our system. So if the score is greater than the 65%, and we are using a redundant, if we are using a redundant architecture and the score obtained by the is greater than the 65%, we are okay. We can say that our design is common cause failure proof. Another point that we have to consider is the systematic failure. So failure related to the design of our system, and the standard gives in an annex, in the annex E2, a set of measures to control systematic failure that must be followed and validated. And for instance, the use of suitable material and adequate manufacturer, the compatibility between selected component, the design modularization, as I said before, separation of software related safety related software and non-safety related software, the use of proven design principle or of standard interface. All the prescription reported in the annex helps the manufacturer to design a system that is more robust to systematic failure and to obtain a greater, a safer system. The last part, the standard gives more than, in addition to all the prescription about the design and production, give also the prescription about the verification and validation. So a list of validation and verification activities that must be performed, and they are reported in the part in the standard. And there are specific activities that involves the test specification, the hardware, the software. So verification activity on the design, for instance, the use of VNV methods, the testing, black box, HIL, hardware in the loop, machine testing, analysis, and other document that manufacturer must produce in order to ensure the safety, that all the safety requirements have been fulfilled. You can see there is a verification list, and depending on the performance level of our system, the verification and validation activities can be carried out by the team that is in charge of the development of the system, by other departments of our other department of our company, or by an external assessor. For instance, in maybe for the AgPL D or E, we can see that that the work product must be checked and verified by other people of the department of our by other department of our company, or by other team from or an external assessor. So is no it is needed a more detailed verification of all the phases of our development. See, the safety audit or a safety plan validation, the safety documentation review is not required for the AgPL A, which is the lowest performance level, but starting from the AgPL C, it's required that the team or a person performs the safety documentation review. And we can give as well as the safety audit or the safety plan validation. So with this slide, I concluded my presentation. I hope to is only a quick because we have a short time. Is a quick overview of the ISO 25119